Hey guys, Dr. Peacock here, hoping to provide you a little bit of a normal chemistry experience by doing an experiment, okay? This week's topic is chemical equilibrium, which has to do with chemical reactions that are reversible, okay? Usually when we look at a reaction, there's a one-way arrow pointing from left to right, where our reactants make our products and then it's done. Okay, but with reversible reactions, what happens is you make your products and then your products turn around and reform some of your reactants, okay? A good example that's not a chemical reaction but is a reversible process would be like taking a sample of water and making ice. You can take water, freeze it, make ice, let the ice melt, it'll make water. Then you can freeze the water again, make ice. Then you can melt the ice again, make water. You know, like that's a reversible process where if you start with water and end up with ice, you can also start with ice and end up with water. It's a physical process, not a chemical change, but it is a reversible process, okay? So we're going to look at this lab called Investigating Le Chatelier's Principle. And the thing about equilibrium reactions is that they like to stay at equilibrium, okay? There's a nice balance at equilibrium. Everything's in just the right amount. And if you do something to the system to stress it out, then what it'll do is it'll shift either to the right towards the products or to the left towards the reactants, so that it can reestablish equilibrium, okay? And that's called Le Chatelier's principle. Le Chatelier's principle lets you know that anything you do to disrupt a system at equilibrium, that system will try to counteract that situation to reestablish equilibrium. So we're going to create an equilibrium reaction in this beaker, okay? And so following along with the directions in the lab, I'm going to put 3 drops of FeCl3 in this beaker. And you can see FeCl3 is like this orange color. Then I have KSCN, which is a clear color, and I'm going to put it in here right on top of the FeCl3, and I'm going to show you in a minute because that's actually really cool. And it makes like this dark red blood type color, okay? Well, we don't need that dark red color. So what we need to do is I'm going to add some distilled water, okay? And we need to dilute it until it's like a light orange color. And that's not quite light enough, okay? So I'm going to add some more water. I'm going to swirl. Okay, that's like a pretty good light orange. Now you might be thinking, well, is she measuring or anything? No, I'm not. And honestly, if you were doing this in class, I wouldn't have you measure either. I would just tell you to try to make a light orange color, and your color might be different than your group's color, but that would be okay. The lab usually works no matter what, which is pretty cool. So then the next step in the directions is to take what you made and try to divide it somewhat evenly between your test tubes, okay? And if you can see, I have the test tubes labeled A through E, all right? So we're gonna look at this, all right? And let me just pour, let's see how I did here. Ooh, almost perfect. Okay, so we have our 5 test tubes. They're about even. They get a little bit more as I go across, but that's okay. It doesn't have to be perfect. It's just for color comparison purposes. Okay, this is actually a system at equilibrium, all right? That light orange color tells you that the system is at equilibrium. So if you were to look at the reversible reaction on your lab, it says that Fe3 plus has a characteristic gold color, that SCN minus is colorless, and that FeSCN2 plus has a rust color, okay? And so gold, colorless, rust, you can see that none of these test tubes are displaying either of those colors, okay? which means it's at equilibrium. It's somewhere in between. But what's going to happen is if we shift equilibrium, remember, Le Chatelier's principle says the reaction will react to counteract that shift. And so what's going to happen is if we disrupt equilibrium, the reaction is going to proceed to try to undo it, okay? And this lab is nice because it shows you that very clearly because you can see the color changes. All right, now, we're going to leave, and I just want you to see, we're going to leave test tube A the way it is so that we remember what that orange color looks like and we have a comparison, okay? Test tube B, the instructions say add 4 drops of FeNO3,3, and I have all my stuff set up here. I just want you to see, this was kind of the bottom of the barrel, but 1, 2, 3, 4. Okay, and right away you can see that there's a color change there. Do you see how that darkened up compared to our test tube A? So clearly test tube B did not like what we did, and it shifted, okay? Now go back to the reaction. What color do you see? Do you see gold or do you see a rust color? Okay, if you see gold, that means it shifted left towards the reactants. If you see a rust color, that means it shifted right towards the products, okay? So this would suggest that it shifted right. And the reason it shifted right is because we were adding FeNO3,3, which means we added more iron, okay? And iron is a reactant. And so it's not happy that we added extra reactant. It wants to get rid of that extra reactant we added. So what it's doing is it's using that extra reactant by making more product so that it can reestablish equilibrium. And as it makes more product, as it uses up the extra Fe3 plus that we added, it's shifting right, making more product, and as it makes more product, it becomes a darker color, okay? And so that's why we're seeing that rust color. All right, test tube C. We're gonna add 4 drops, of KCl, okay? So we're gonna put 4 drops in here. 1, 2, 3, 4, and look at that. Nothing happened, right? Well, that's weird. How come nothing happened? Because KCl didn't disrupt equilibrium, okay? K plus is not part of our equilibrium reaction. Cl minus is not part of our equilibrium reaction. So we didn't actually do anything to disrupt equilibrium, all right? So that's why C stays the same. You would say no change, no shift, because equilibrium's maintained, we didn't disrupt it, and that's good. Okay. Test tube D. See if you can make a prediction. We're going to add KSCN, okay? KSCN is made up of 2 ions, the K plus ion and the SCN minus ion, all right? So take a second and look at our equilibrium reaction and ask yourself, are either of those ions part of our reversible reaction? Is K plus part of our reversible reaction? What about SCN minus, okay? So I'll give you a second here to look at that and decide, all right? And I'll get my test tube ready, okay? And here's the deal. SCN minus, which is called the thiocyanate ion, is a reactant, which means we're adding more reactant. If you add more reactant, what does the equilibrium reaction want to do? It wants to get rid of it. If you add more reactant, it wants to make more product so that it can get back to equilibrium. So if we're going to make more product, what color do you think we're going to make here? Is it going to be gold? Is it going to be rust? Let's see. 4 drops. Here we go. 1, 2, 3, 4. And again, we made that rust color. You can see it's darker than the original tube. Okay, lastly, NaOH. This is actually a tricky one. I'm going to add 4 drops of this so that you can see what happens. 1, 2, 3, 4. Okay, So I'm actually gonna give that a minute because I think you'll be able to see the reaction a little bit more. I'm gonna put my lid back on my NaOH container. Okay, and I'm gonna hold these up really closely so that you can see, okay? Do you see that test tube A looks more orange at this point than test tube E? Can you tell that this is a more yellow color than this one was? Okay, that's because, and this is a little advanced, but I did want you to see what would happen if it shifted. Oh, oops, nothing spilled, no worries. I did want you to see, I always talk about not flapping your arms in the lab. So what happens is I did want you to see a reaction that actually shifted left, okay? I'll explain a little bit about why it shifted left. The reason that reaction shifted left is because the hydroxide ion in NaOH, which is the OH minus, will react with the iron, Fe3+, and when those two react together, they actually make a precipitate. And what'll happen if we had time, like if we were in the classroom and I was able to show you this the next time you were here, but I'm not going to be able to because I have to clean it up, you would see that there was actually a precipitate at the bottom, like the Fe and the OH got together and they made a solid compound, and over time that solid compound would fall to the bottom of the test tube, okay? And the solution that was remaining would be yellow. And the reason it would be yellow is because when that OH minus reacts with the Fe3+, forms a precipitate and falls to the bottom, it's actually taking the iron ion away from the equilibrium reaction. And the equilibrium reaction wants to be at equilibrium, which means it needs to make more iron again. So if the OH minus pulls some of the iron ion out, then the reaction needs to shift left, okay, to make more iron, which is why you're seeing that gold color that's characteristic of the Fe3+, because this is making more reactants to compensate for the iron that just got removed from solution, which we can't see because it's so small that right now it's like not visible to my eyes or the camera, and it would fall down to the bottom of the test tube, and if we were able to come back, we would be able to see it. But I'm not, so we can't, so you're just gonna have to take my word for it. But you do see the yellow color, so you can see that it did shift, okay? So that is our Le Chatelier's principle lab that hopefully you at least enjoyed watching if you didn't get to do it. And hopefully we'll be able to keep doing activities like this to make it feel like a real class, okay?